morning, engineering 2. Woo. Can you guys hear me? All right, so in terms of what we're doing today, we are going to continue talking about GD&T, but we are moving away ourselves from, I don't know if you guys recall, the way we started. It's like here. Go here. Go here. The way we started, we first introduced you to GD&T and give you the importance of it. Then we talk about form. And if you guys recall, I told you guys about flatness. And I also briefly introduced you to circularity. And there are other ones as well, but we didn't cover them. Right after form, we introduced you guys to orientation. And orientation was parallelism. We also talk about a little bit about perpendicularity and as well as angularity. Right? Parallelism, perpendicularity, angularity, flatness, and circularity. So now we are moving away from orientation, and we are going to start looking into position. But before we start into position, we gotta go back into the form. So we're over here because I want to talk to you guys about straightness. And straightness is going to give us the tools to then start talking about position. So we will stop in straightness. This is a type of a form of GD&T symbols, and it will give us the knowledge for us to understand position. Okay, so let's start. And let's start with straightness. Okay, so as I previously told you, if you guys were, and I'm not sure if I brought my cheat sheet, but let me see if I can find some sort of for a lesson cheat sheet. I think I left it on the engineering lab. Well, maybe see if I can find an electronic file that we can share. We can talk about it. Let me see here. Come on, computer. Come on. Is it going or no? It's coming. Okay. I'm going to look for it so we can show you some of the stuff. I give you like a cheat sheet that talks about position. What's going on with my computer? There we go. SJDC. Too many files here. Come down. And then come down. Professor. And then engineering 2. And somewhere in engineering 2, I talk about form tolerances. Let me open this guy. Open with Adobe. Right. So if I look at the cheat sheet, and again, you guys should have not a color one because I give you guys a black and white. If you guys want to get it in color, you can always print it. You guys have seen here, these are the form tolerances. And again, form tolerances are these ones, the one that we started with. You got the flatness, and we briefly talk about circularity. So you guys have a cheat sheet for form, and even tells you on the right side is form. They talk to you guys about the feature datum control frame, what's a datum, what are the degrees of freedom, what's a tolerance zone. They talk about rule number 1, which we're going to talk about today. We have also talked about the maximum material conditions and the least material conditions. Virtual condition and bonus tolerance is something out of the scope of the class. It's a little too complex to cover it in such a short time. But again, in order for you guys to understand position, I need to talk about straightness. You guys will notice there are two types of straightness. Straightness of a surface and straightness of a derived median line. So let's start with the straightness. So straightness tolerance may be used to control the straightness of a surface elements or a straightness of a derived median line for a regular feature of size. Remember, you got two types of features: features of size, features of surface. So for example, like the one that you guys see here is trying to control surface, how straight the surface is. So if I were to simplify this in terms of what is a straightness in a surface, let me come up with a little sketch. Instead, I have a square, and then I have my front view, I have my top view, and I have my side view. Okay, and let's say that I want to control the straightness of this part, and I want to make sure that it's straight. Well, if you guys want to look at the surface, well, the surface is going to be imperfect, right? It's going to look like wiggly all over the place. Okay. Flatness, if you guys recall, flatness is two parallel planes. Actually, it's like two parallel planes parallel to each other, and my part gets to live somewhere in within it. Well, straightness is a little bit different. Straightness is just how straight the part is. So instead of being a 3D tolerance zone, this is flatness. The straightness just say you know what? I just want to make sure this is straight in a single direction. So how wavy the part is, and it's actually a 2D tolerance zone. So kind of like I put a line on the bottom and a line on the top. And my path, as I go across the part, needs to be straight with this 2D tolerance zone. So if I want to look at my dial indicator, which has the little dial, and again, if you have this spring-loaded pin that you touch the part, and then you just have to move it straight the direction. So you gotta let it know on what direction you want straightness. For example, in here it seems to me that I want straightness this direction, so I will have to go to the side where I see it because I want straightness this direction. You see it? This is the side view. I'm looking this way, so you will show it where you want the straightness. And then you gotta call it. So you put a feature control frame, and then you will say, okay, so how do I put the straightness? So straightness just looks like a line, just straight. And then you just go and give it a distance, I don't know, 0.01. Keep in mind that I'm just looking at straightness in a single direction. I have no datums or nothing because it's a form. I'm just controlling the form. So straightness of a surface, it is two parallel lines separated apart by the indicated distance on the tolerance zone. My part gets to deviate along these two parallel lines, and they are independent of each other. Okay, so if I were to look at it, if you were to make the measurement, if I go and I grab my dial indicator and I just move from this line, which I just made here, and I want to check the straightness of the next path, I will have to lift up my dial indicator and let the next measurement. Right, each of measurements is independent of each other. Okay. Okay, so if I were to put a look at it in the front view, this guy is my tolerance zone, like 2 points, right? Because they run across. So my dial indicator will go in and out of the page in this view, independent of each other. Okay? That is what straightness is. The tolerance specifies how close the perfect straight a feature must be made. The allowable form variation for any straight surface may be controlled with this type of tolerances. The form of the derived median line is called the axis straightness, and is based on this SAE Y425 standard. For a regular feature of size, such as shaft, may also be controlled with the straightness tolerances. Again, for a feature of size, let's finish first features of surface, and then we can talk about features of size. The example that you guys see here, you point to the part that you want to make it straight, and give it the tolerance zone, where is the separation, and the seam. I usually don't like, again, this guy, I don't really like to do it. For a surface, I usually like to have this guy on the side. I think it's cleaner, right? You might see some people doing like this. I'm just speaking. So in you guys' case, don't do this. Just do it like this. Since I'm the one grading, follow my standard, right? Okay, so this is the same image that I was telling you guys about, right? When you guys have a part and you have flatness. Flatness actually, again, is a 2D, it's a 3D tolerance zone, right? You have two planes parallel to each other. Where straightness, it is a 2D tolerance zone. It's kind of like two lines on top of each other, and the part gets to live within it per pass, right? So this is what you guys would see like this orangey, right? Which says 0.05. Well, that's the distance that is indicated on your feature control frame. And the yellow one, it seems to me it is flatness, right? And if I want to use both of them, that means that I just have a refinement on one within the other, okay? And again, at that point of time, you might have one within another. It's just refinement. All the form tolerances are refinement on each other. So again, I could have a part, right, which has a distance. Let's call it this guy 1.00 plus minus 0.10, right? That means that I have a tolerance zone here. Yes. And then I might also have flatness. Let's say common flatness here. 0.05. Right? So it's a little bit smaller than this guy, right? Because this is 20,000. I mean, 200,000, 1,000 up, 1,000 down. I mean, 100,000 up, 100,000 down. So 0.1 up, 0.1 down. This guy was telling me, you know what? Within your tolerance zone, the flatness will say, within your tolerance zone, your part gets to live within two parallel planes that are 0.05 away. Okay, what happens if I do another one? Maybe I have a straightness of a surface, and then I say, you know what, this guy has to be between 0.01. That means that every pass, and again, it depends on where you put it, right? In this case, you put it here. So that means this direction, it has to be straight independently of each other, like just like this, right? Just go up and down. So you have a tolerance, and then between each of them, this direction, you have another 0.01, independent of each other. So one tolerance zone within another tolerance zone within another tolerance zone, right? So you can, depending on what you want. Right now, I'm just showing you. If I were to have a function, actually, all of this you use GD&T for function. That's the only reason. Do not use GD&T if it's not for function. Otherwise, you're just making the part expensive. And especially some people don't understand GD&T, so you might confuse them. Let's continue. You can also do a straightness of for a cylindrical part. You guys will see it here. The straightness of a cylindrical part. The straightness of a cylindrical part. And as I previously showed you, the straightness lives within the size tolerance zone. This is what we call it rule number one. Rule number one. And as I previously have said before, it just means perfect form at MMC. And as you move away from MMC, you have allowance for have a form variation. For example, like the one that you guys see here, you have 0.875 plus minus 0.05. So you have upper limit and lower limit. Right? So I'm going to assume that this guy is the upper limit, is 0.880. So that is the maximum that you can have because it's the maximum material condition, right? Perfect form MMC. So you are allowed to have variation. And if I were to put this line here in the middle, and this guy here in the middle, right? You see it? This guy here in the middle, I have my maximum limit and my minimum limit, right? 0.87 and 0.880. So I have a variation that allows to be on the top and a little bit to be on the bottom. Okay, so in here, each of these lines is independent of each other. So every path that it goes in terms of straightness, it will come with my dial indicator, and it just go straight the rod. In this case, because it's a cylindrical picture, my dial indicator just will move in this direction, right? So if maybe I can draw my dial indicator. My dial indicator. Let me grab it and let me move it, right? So I will go across the part and start seeing the variation of the needle, right? So for example, in here, as I move across the car, each of the line distances is independent, and they have to be within 0.006 of an inch. Okay. As I previously told you, it's dependent on rule number one, and rule number one says perfect form at MMC. Max, the perfect form MMC. That means once I get to the limit, to the MMC, I cannot grow anymore. So otherwise, I will violate my size tolerances, my plus and minus. For example, here, let's suppose that this 10.05 is the maximum material condition, so the biggest I can get. And somewhere in there, I have a straightness of 0.1. Okay, so if I were to look at this and the shape that this guy came about to be 10.05. I went over here, and this guy, it seems to me that I got kind of like exceeding, right? If this guy is 10.05 is the biggest I can get, and then it's out of the range, so it's no bueno, because I can only vary to 10.05. In other words, if I have a part that is like this, it can vary, let's say plus and minus. It can vary all the way up to the maximum material condition. And again, I'm assuming that this is an external feature, MMC. Okay, this is the limit that I can go in terms of size. Otherwise, I will violate my plus and minus, my size tolerance. My part that gets to live will have to live within the maximum and the minimum material condition. So I might come over here in terms of this guy, and I might come here in terms of this guy. So in here, you guys could see that there is a form variation that is allowed because I am within the tolerance. Now, if I go and I apply in here straightness of 0.01, the tolerance zone of this guy will still have to fall within this region. So let's suppose that my part came up to be, when it got fabricated, it came up to be like this, like that. And in here, I have, I don't know, 0.001, right? Well, these guys tell me, hey, you have to be straight between 0.01, and here I only have 0.001 of form. Well, I cannot violate my MMC. I have to be within only 0.01, even when this guy is telling me that you have 0.01. And if you guys were to violate it, if it were to actually grow more, be 0.01, well, it exceeds my MMC. Therefore, it's not bueno. So sometimes think about it like the envelope. Think about it. Sometimes they call it envelope principle, right? And if you have a letter, the letter can go small or it can go big. And the form variation of my letter or my part has to live within this envelope. And the envelope is the maximum material condition. If it's small, it can fit in there and it can move around it and also have form variation. But its maximum material condition, the biggest it can get, has to be within the envelope. Now, when the letter that's going to go in the envelope is all the way to the biggest it can get, in fact, is as big as my envelope, well, the letter will not have, we cannot have any form variation because it's already at its maximum material condition. So there cannot be any wiggle room or no imperfection because it's already at its worst case condition. Okay, that is pretty much rule number one. Okay, this is the verification of surface straightness. As I previously told you, it's in each of the paths is independent of each other. In this case, it seems to me that I have a straightness. Let's go with computer. There we go. One method of inspecting the straightness of a surface elements, as shown, the part is set on an inclined sign bar. The sign bar is inclined on top of the flat plate or surface table by placing gauge blocks under one of its feet. So gauge blocks are just pieces of metal that are calibrated to be really accurate. Measurement of a straightness variation should not require a specific orientation, again, because it's form. Nowhere within my feature control frame had an A or a B referring to a perfect condition, right? All of this is back to datums. So flatness doesn't have a datum in the feature control frame, or circularity, or straightness. None of them, because they only control the front, how wavy the part is. Not required for a specific orientation of the part during measurement. Therefore, the angle of the sign may be adjusted to minimize the dial indicator reading. The dial indicator is moved in a straight line along the surface. This is repeated for several locations. The variation measurements of each pass of the dial indicator are considered separately. Remember, it's kind of like a 2D tolerance zone where I have two lines parallel to each other, and each of these measurements is independent. Okay, now we have covered a straightness of a surface. It's a 2D tolerance zone or two parallel lines. You don't have datums. The tolerance must be less than the dimensional tolerances. Yes, because it's a refinement. All points along each line element must lie within the tolerance zone. You guys can see here, this wiggly red line has to fall within it. Let's go into the one below it, which is the straightness of a derived median line. So, the same way, like I told you guys before in the beginning, which we're talking about vocabulary, and again, all this GD&T is kind of like a language. You speak español, or you speak GD&T. Right? How do I know I have a feature of size? Well, because I apply my feature control frame on my feature of size. As soon as I put it on a feature of size, it's something different. It doesn't mean the same thing as before when I apply it to a surface. Now I am controlling the features of size. In terms of straightness, you are controlling the derived median line. So what does the derived median line mean? It means if I were to look up a part, my part gets to be like this, like that, right? Well, previously told you that if you have a straightness, you are bounded by rule number one. Okay, but if you have a straightness on a feature of size, so a straightness on a feature of size, this automatically allows to break rule number one. Before you were confined to the envelope, right? Before you were confined to this envelope, and then you have your letter that was there and it had to be perfect at the envelope condition at MMC. Well, now, if you put this on a feature of size, which in this case is a diameter, right? So I went and I put a dimension here, diameter, and then right next to it, I put the feature control frame and I put straightness. It allows you to open up your envelope. Now your envelope is open and allows you for your letter to have out of straightness of the derived median line. Okay, so before we can understand a little bit more about the derived median line, let's talk about what is the derived median line. So, the derived median line pretty much tells you, okay, I'm going to grab my guy and I'm going to measure. I'm going to squeeze along. Let's say that I have a chalk, like a drill gun I have used before, and I'm just going to squish. and it's going to derive, it's going to find my axis. It's somewhere there. And then I'm going to move my chuck somewhere a little bit along the line, and it's going to have another one somewhere there. And then I go a little bit more line, I'm going to have another one there. So I'm going to squish independently, try to find the axis independently. So I'm going to go somewhere there, somewhere there, somewhere there, somewhere there, somewhere there. And if I were to combine them all together, this guy is what we call it the derived median line. Okay. So when we use a straightness on a feature or surface, this is what we are trying to control. How straight is the derived median line? Okay. Up to the straightness should be fairly straightforward. If you place a straight edge on a surface element with a straightness tolerance, any deviation of the surface must be straight edge, must be less than the tolerance. We indicate the surface element's straightness tolerance by putting the feature control frame on an extension line, extend to the surface, or at the end of the leader point to the surface. So that was the easy one that I told you. Things get a little bit more complicated when we look at straightness of a derived median line. First, there is a difference of how we indicate the tolerance. The feature control frame is associated with the features of size. Therefore, you need to put it on a size dimension. Also, it has a little m, right? And we will talk about m in not too long. What does it mean? What does it mean when you put an m on a feature control frame? Let me see. What do I have here? Straightness with MMC. Oh, it's already telling me. Explain it. Straightness with MMC is kind of like an if and else statement. If your part gets to live, actually I want to make a drawing. Actually I have a drawing right here. If your part, which has a size somewhere over here, right, it gets to come at MMC, I am going to give it 6,000 in terms of tolerance. So let me actually try to see if I can explain this in sketch format. So let's rewind, and we're gonna put my pin. Put my pin. Put it there. Put it there. Put it there. And it has a maximum material condition here. Seems to me 0.76, right? 0.7 diameter, 0.76 here. Okay. 0.75 plus 0.01, 0.76. It's telling you, you know what? When your part gets to come at the worst case condition, which before the part MMC was my size of my envelope, right? The part has to be because I have to follow rule number 1. But now because I apply it to straightness, it allows me to violate rule number 1. And I'm going to tell you how much I'm going to allow you to violate it. And how am I going to tell you how much I'm going to allow it to violate it? With the feature control frame, which is telling me 0.06. So it's telling me, you know what? When you get to this condition, I'm going to give you 0.006 out of straightness. So I'm going to allow you to violate it by this amount. That's pretty much what it's telling. Your out of straightness is allowed to be, when your part comes at MMC, you will get 0.006 out of straightness. And that's where the M comes about. If your part's at MMC, use this. But the first thing you should notice about the figure is that the diameter symbol appears in front of the tolerance zone. Yes, because what we are controlling is the derived median line. So if I were to look at the derived median line, whatever I put in my feature control frame, and I put straightness, diameter 0.006 at MMC, this guy is the size of my tolerance zone. In fact, my tolerance zone is a cylinder. Like this is my cylinder. Boom. And in this case, my cylinder diameter is 0.006. I am controlling the straightness of my derived median line within 0.006. The second thing that you should notice about the above figure is that the feature control frame includes the maximum material condition modifier. No modifier were used with the surface element straightness tolerance. This modifier indicates that the tolerance zone 0.00C applies only when the size dimension is at MMC. If the size dimension is not at MMC, the size of the tolerance zone changes, which allows you to get bonus tolerances. In other words, I told you, when you use the straightness in a feature or surface, it allows you to break rule number 1. I'm telling you, this is how much I allow for you to vary out of the rule number 1. Well, keep in mind that in this part you also have an LMC. Okay, maybe your part did not come up to the MMC, maybe it came over here to the LMC. Again, this is LMC. This is MMC. Okay, and this is the variation that I give you within my feature control frame. Well, if your part gets away from MMC, it means it gets a little bit smaller in this case, I am allowed to have extra variation because now I can come, and if I go all the way to LMC, my part gets to vary even more, right, in terms of form. Is here. So because I am moving away from MMC towards LMC, I get bonus tolerance in terms of straightness for my derived median line. Hopefully that makes sense. This is row number 1. Now in a proper format. In fact, if you guys want to go to the standard, it's a couple of paragraphs. We just try to, I'm trying to summarize it, simplify it as much as possible. In order to understand how the MMC modifier changes the tolerances, we have to understand the new concept, which is rule number 1. And in here I have a summary. I think this is a book. This is not the standard definition, but it should help me try to explain exactly what I just told you. Okay. Let me see. Come on, computer. Rule number 1 requires that the regular features of size have perfect form at MMC. I think about it like the envelope, right? This establishes what is commonly known as perfect form boundary at MMC. No element of the feature may extend beyond the boundary. This requires that a round hole be perfect cylinder when it's at smallest permissible diameter, and that a shaft be a perfect cylinder when it's at largest diameter. However, remember I told you, if I put it on straightness, I can violate rule number 1. So let's actually think about it. What would happen if I don't have a symbol that says straightness in my part? In other words, I keep this guy as rule number 1 it states. Come on, computer. The size feature, come here. As the size feature departs from MMC, the feature is permitted to have a form variation. Form variations are not permitted extend beyond the perfect form boundary. And this is what I pretty much told you when I talked to you guys about the envelope. Right? This is just kind of like a recap. Right? The book is trying to explain you what is MMC. Right? This is what I told you. If you have an envelope, right, and I have an MMC and LMC, I cannot have variation when my form is at this maximum material condition. So I put it here in a speed. And again, the size of this envelope, is an MMC. Okay, my part comes from MMC. Well, I cannot have form variation. If I have a LMC or away from MMC, right, towards the smallest size, I will have form variation. And this is what is training you. Okay, so here I have form variation, and here I have form variation. But again, at the end of the day, I need to keep myself. If the above figure, if the part is uniformly made at LMC, the smallest diameter, then it may have an axis out of straightness equal to 0.01. In other words, I can move away from MMC. Whatever I give you, actually can get it as a bonus. I will do the math in just a second. Hopefully, it will make a little more sense. Straightness without MMC. Let me see. Straightness without MMC. I remember this is what it's telling you. If you go and you put a straightness with a diameter of 0.002 is controlling the derived median line. The cylinder, it is 0.002. And because I do not have a M, it's telling you it is the default value is RFS. So the same way that you guys have MMC, diameter 0.01. If your part comes at MMC, you get 0.001 in terms of this cylinder I'm talking about. If I put LMC, if your part comes at LMC, you will get 0.01. And if it doesn't have anything, doesn't have any M, the default is RFS, regardless of feature size. In other words, I say, you know what? I don't care if you come at MMC, I don't care if you come LMC, or you came anywhere, it doesn't matter where you are, regardless of the feature size, your tolerance zone will always be 0.01, which in this case, in terms of your example that you have here, is 0.02. Regardless of how it comes, it will always be 0.02. Okay, so a little bit too theoretical. Here I have an example, and hopefully we'll wrap everything up. It will make a little bit more sense. theory, but I'm sorry, you guys need the theory so you guys can understand position. Now, let's have an example, and hopefully the example will make a little bit more sense. Okay. In order to understand the interaction between axis straightness tolerances and the diameter tolerance of shafts and holes, we need to start with design intent. In other words, let's think about application. There are two main types of axis straightness tolerances identified by the modifier used after the tolerance. There is the non-modifier, which is the regardless of feature size, and the tolerance is independent of the size dimensions. In other words, regardless of the feature size, I'm going to give you this, and this is what you're going to use. That's what RFS stands. And you don't put anything by default. An RFS axis tolerance might be important for rotating cylinders or for a cylinder being used as a linear guide. The maximum material condition modifier M is often used when the intent is to fit a pin. You guys remember when we were doing fits, and I told you guys the biggest the shaft, the smallest the hole, that is the M. The maximum material condition is the worst mating condition. Well, the same concept over here. When you are putting M, you indicate at the worst case condition, I'm going to give you this out of straightness to take care of the geometric imperfection. So it's accounting for the worst case condition in terms of geometric imperfection. They just put it in the feature control frame. Consider the following figure, which shows a hole and pin designed for a clearance fit. So this is the example. Let's say that I have a pin, and this pin has to go in a hole. Well, if I were to look at the size of the pin, here I got 0.500, 0.590, 0.500, and 0.510. Okay, so I have a MMC and LMC for each of them in terms of size. The pin has to go in there, and it seems to me like at this point of time, if my part will come in terms of the worst size here and the worst size here, theoretically it should fit, right? However, there might be cases where my part, if I were to measure it, if I were to measure the part, and it will come up a little bit crooked, like it might come, right? Like in reality, it will come. And if I were to measure it, it might still be okay. So if the designer has sized the part so that even in the MMC condition, the part will just fit together, the 0.500 will fit into the 0.50 hole. But what if both pins and the hole are out of straightness? Let's say that I measure the pin, and my pin now it looks like this, right? And I measure it here, it's within the boundary. And then I measure it here, so in the bound within the MMC LMC, right? The biggest and the smallest. Good, 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 good. Let's say that every application matches. However, because now my pin is crooked, it actually acts bigger. If I were to put the pin, which is this size, in a hole that is this size, I cannot fit it because in reality, this pin now acts bigger, as big as this. The out of straightness. So while the size accounted for size imperfections, you have to do something to account for geometric imperfections. Because if you just count for size imperfections, you might be passing a part and then try to put it over there and it will not fit. The same thing would happen with a hole. If I were to look at the hole and the hole get to bend or be like bowed within my part, the hole will act smaller. I cannot put a pin, make a pin right here, which is perfectly straight, and I want to put it inside. Well, it will not go there because it's pounded, right? It's bowed. So what we're gonna do? How do we fix this? Well, remember, now that you guys learn about the straightness, we can account for the worst case condition. And the worst case condition pretty much tells you, let's account for geometric imperfection. Let's just not account for size imperfections alone, but let's work with both of them at the same time. Let's account for the size, which is the biggest it can get, the worst case mating condition, right? Between the hole and the pin. The worst mating condition will be when the hole is the biggest, and let's also add the crookedness in there. That will be the worst case condition. The biggest plus the crookedness. And let's do the same thing with the hole. Well, remember the hole became smaller when it was an MMC. But guess what? Once I bow it and I give it crookedness, my hole even becomes even more smaller. So let's take care of that. Let's account for the worst case condition of the pin and the worst case condition of the hole. And let's call this guy something. We're going to call it the virtual condition. The virtual condition, it is the worst case condition accounted for size and geometry imperfections. When the hole is the smallest, and even take away the geometric imperfection to make sure that you get this the minimum you can get, and then grab the shaft and make a V with MMC and add the geometric imperfection. This is what we call it the virtual condition. And the virtual condition says, let's add it all together. Let's put it all together, and then we can make this guy function. So let me see over here. Come on, computer. So for example, right now in here, now I have a pin that has been fixed. And let's make sense out of this little graph, this little image that I gave you. And then we're going to stop it right there. So let's try to make this out of sense, right? So if I were to have a pin, which I want to make into a hole, and I have the LMC and the MMC, right? So what's the worst case condition for a pin when it's the biggest? 0.490. Okay. Let's add the imperfection, the wiggle room. Let's say that my wiggle room, the maximum I'm going to give it, it is 0.005. So if I were to account for both of them, and imagine that I have a pin which has now the combination of both geometry and size imperfection, right, all put together, this guy will be 0.495. This is my virtual condition. The worst case condition put geometry and size imperfection together. Now let's do the same thing with the hole. Okay, now I have a hole. In my hole, when I was at its LMC, okay, so when I was at its LMC, let's say LMC is right here. Remember, you have MMC and LMC. Let's say I'm in LMC and MMC. When the hole was at MMC, it was good. But as soon as I started making a cricket, it became even smaller. So let's account for that and make the hole even smaller. Accounting for that geometry imperfection. Geo imperfection. And we're going to give this guy, and we're going to be at 0.005. Right? So now what is this? The hole at this worst case condition. What is the smallest? Another word, 0.500 minus 0.005, which gives me 0.495. Virtual condition. If I can grab that pin and make it big and make it as cricket as I can make it, grab the hole and make it small, and take away as crickedness that I could make it, so it becomes as smaller as I could make it. And if this guy, which is the virtual or the worst case condition, and this guy are at least the same, or this guy is a little bit bigger, because I allow for some allowance even after the crickedness, I will guarantee that there will be assembly at the worst size condition and at the worst crickedness condition. This is what a virtual condition is. Okay, we will continue next time. We'll have a couple of slides in terms of allowing you to know what is bonus tolerance and a little bit about functional gauges. And then right after that, next week, most likely we will start with, actually we might do a little review on this in the lab. Maybe I can finish these 4 slides in the lab and we will start next week fresh with position. Let me stop my share. Let me stop. You guys about rule number 1, virtual condition, bonus tolerance, and functional gauges in person. It's easier when I explain this in person than me on the computer. So I would turn off the monitor, please. So I would expect you guys pay attention. So when you guys have your quiz, you have to understand what I'm saying. Okay. Okay. Let's start with rule number 1. So when you guys have a part, either being an external part or an internal part, like a hole or like a pin, you guys are bounded by your size dimensions, your plus and minus, okay? Which give you guys your upper limit and your lower limit, depending on what you guys are doing. Are we good? So your form, how wavy it is, how straight it is, it all depends on those plus and minus that you guys have. That's out of the, without you doing any GD&T, you guys are already bounded by those limits. Does that make sense? So your form is already bounded by that. So what is happening is when you guys get a part, and your part gets a GD&T symbol on it, which is a refinement in terms of straightness, in terms of flatness, in terms of circularity. It's just meant to be a refinement. But what happens if you're already all the way to the top, to the biggest that your size could be? Maybe you are at MMC, the biggest material that you can have. At that point of time, you are all the way to the top. You cannot have any form variation. Does that make sense? Okay. Now, this is what we call the envelope principle. That means if you guys were to imagine an envelope, I don't have an envelope, some of you guys have an envelope. The envelope, and I'm going to think of an external feature, but it could also be for an internal feature. So let's suppose that I have an envelope, right? And that envelope has a certain size. The biggest that this envelope is going to be your maximum material condition. Let's think about your part, which is going to be this green sleeve, can be small and big. You have your upper limit and your lower limit, right? I'm going to make this envelope the biggest it can get. Well, the maximum material condition. Now, let's suppose that my part came at its least material condition, the smallest it could be. I can grab my envelope, open it, grab my part at the least material condition, stick it in there, and then we'll have a lot of wiggle room, right? A lot of form deviation that I could have. Let's speed it up. Let's say, you know what, now I'm not going to do to the least material condition. I'm going to make it at the worst material condition, which is going to be at the maximum material condition when it's the biggest. I'm going to grab this guy and I'm going to stick it inside my envelope. What happens? Can it move? No. Can it have any form variation? No, because as soon as it has any form variation, it's going to get out of my envelope. Does that make sense? That's what it means. The envelope principle is perfect form at MMC. And as you move away from MMC, you're allowed to have a form variation. But you are capped at your MMC. That means if I went and I put it on the GD&T and I say, you know what, have circularity of 10,000ths of an inch, but your part came out and you can only have 5,000ths, you can only get 5,000ths because you are bounded by your envelope. Does that make sense? Perfect form at MMC. Okay, now that was MMC, rule number 1, which I try to explain it during the class. Hopefully, it makes a little bit of sense. And then right after that, I talked to you guys about straightness of a surface, and straightness of a derived median line. The straightness of a surface is easy, and I won't go over it. You guys watch the lecture if you guys didn't watch it in the morning. The straightness of a derived median line is a little bit more complex. That's what I want to go over in class. So the straightness of a derived median line, which is here, straightness of a derived line. Remember, you have two features. You have feature of surface and features of size. My nose is a feature, my eyes are a feature, my cheeks are a feature, my height is a feature. Okay? So when you guys see something in the drawing, and the drawing has a dimension associated, especially in terms of width, or in terms of if I were to have like a width of something, or maybe you have a slot and I'm measuring the width of the slot, maybe I have a diameter that I'm pointing to, that is a feature of size. That makes sense? If I am controlling the surface, like flatness, I'm just pointing to the surface, say I want it to be flat. I'm not controlling a size, I'm controlling the surface. Got two types, feature of surface, features of size. So for a derived median line straightness, what you are trying to control the straightness of a feature of size, you're trying to control the derived median line. So what does that mean? Let's suppose that I have a part that looks like this, and I went and I placed this pitch control frame of straightness, and I put it right on a feature of size. Well, do you guys remember the envelope principle that I just told you guys about? When I have a feature control frame of straightness applied to a feature of size, automatically overrules rule number 1. So you cannot use it. You're allowed to move out of your envelope. In other words, whatever the envelope was before, I get to open it. That makes sense? Okay. So let's talk about the derived median line first, so we can actually talk about this. How do you measure the derived median line? So if I want to have a part that is crooked, I will measure it, and I will get a point from my axis. I will measure again, and measure again, and measure again, and you kind of travel those points, and you try to come up with an axis. Actually, like a line, like a wiggly line. When you guys are putting a straightness on a derived median line or a feature of size, you're trying to control how crooked, how straight your line is in 3D space. Your derived median line needs to be within a cylindrical tolerance zone. If you guys want to look at it, you have a diameter. If I want to control this, I will have a diameter that is 6,000 that runs from here all the way over there. Your derived median line needs to live within it. The straightness is a form geometric tolerance. It means it only controls the form, not the orientation, not the location. Just the same way that flatness controls the surface, and it wasn't oriented to any datum, was the same concept with the cylinder. The cylinder could be anywhere in space. As long as it's 6,000, and your derived median line falls within this cylinder, then what will be instead? Does that make sense? So by me making the cylinder small, I'm controlling how straight my derived median line is. Does that make sense? Okay. Remember that I automatically override rule number 1, which is the envelope principle. Bueno? Okay. Now, let's actually try to make sense of this guy. Let's say that I have a hole and I have a pin that looks something like this. Okay. And I apply the maximum material condition on the straightness. Let's imagine that this is a cylinder or a pin and it's a hole. And in there, I went and I apply straightness here. Here, I'm going to show you, but imagine that it's already there. If I were not to look at the feature control frame at all, and if I will say, you know what, I want to make sure that this pin goes into the hole, you will go to your table, right? You'll say, okay, I want a clearance feed, maybe I want an interference feed, I want this type of feed. Let's say that is a clearance feed. You will say, you know what, I have the smallest it can be and the biggest it can be. Smallest it can be, the biggest it can be. In this case, the worst case condition is the biggest pin and the smallest hole. Right, you can see it? And theoretically, this side will be 0.5 and 0.5, this side will go in. Theoretically. Actually, I want because 0.5 and 0.5 will not actually meet, but theoretically, it will go in. One, okay. These guys is just considering the size itself, like you guys have been doing. But what is really happening, right? Things are not always straight, right? They're never straight. Is that correct? They're never straight. So if I were to look at the same pin, and I want to measure here, and I say, hey, is within my boundary 0.9 and 0.5? Yes. I measure yes. 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 This one is the size that I want? Measure? Yes. 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 So just measure it. And then you wonder, okay, so now let's build it. Let's put it together. You grab the pin, you put it in there, and you shoot, man, it doesn't work. Why? Because it's not straight. I did not account for geometric imperfection. So while I counted for size imperfection, I did not account for geometric imperfection, which is out of straightness. Do you guys see this? So I need to account for this. By me going over the envelope principle, grab this guy, making it big, put it inside my envelope and open up my envelope. Now I have a little bit variation in terms of geometric imperfection. Well, I want to account for both of them. I want to account for size imperfection and geometric imperfection. Put it all together. This is where GD&T comes about. GD&T. Geometric imperfection, dimensional imperfection, put it both together and you get a tolerance. Geometric dimension and tolerance. Okay, so now, remember I told you guys that before, you know me, but now I'm accounting for an imaginary boundary. And that imaginary boundary accounts for that imperfection. You see? A little bit out of frame. Now, my pin, it was big and then crooked. So the worst case condition is when it's the biggest and the crookedest. The maximum material condition plus the geometric imperfection that I give it out of straightness. Okay? My hole acted a little bit different because if I want to put my hole at its maximum material condition, as the bends within the part, my hole actually becomes smaller. So I want to put up a pin that's also straight, which the other one looks a little bit better for explanation. Right. If I want to here, so if you want to go this pin which has the maximum material condition, if you want to try to insert it, that's it, man. You cannot go any further. You guys see it? You cannot go any further. So your hole actually became smaller, and it became smaller by its imperfection. Do you guys see it? So if I want to account for the imperfection and the size tolerance, I need to make my hole smallest, MMC, the worst case meeting condition. And I also need to take away that geometric imperfection, because the geometric imperfection has my hole become smaller. Does that make sense? So if I put all this together, and I get to create a boundary that is going to account for the worst case condition, the worst case condition. when I take care of the maximum material condition, which is smallest hole, minus the geometric imperfection, I will get to the size. And if I can make this side, which is the maximum material condition plus the geometric imperfection, I will get something like this. Now, we need to account for this, and we're going to call it something. We're going to call it virtual condition. Virtual condition is the worst case accounting for size imperfection and geometry imperfection. So, let's imagine this. How would I make something fit? Make it, let's go from the pin, right? Make it big and make it crooked and account for those imperfections together. The biggest I can get plus the crookedest I can get. And come up with a size. Let's call it virtual condition. Okay? For a pin. Then go to the hole and say, you know what? I want to make it small. The worst case condition is the smallest for fitting condition, right? So I want to call it the smallest I can get. And because remember, as I was getting crooked within the hole actually acted even smaller. So let's make it the smallest I can get minus the geometric imperfection. That will make the hole even smaller. Now, how do I guarantee assembly? Go and make the pin the worst case condition and the hole the worst case condition. And even after the worst case condition, this guy still matches and it fits all together, I will guarantee assembly. Do you guys understand? Okay. Okay. So you guys will notice here that now, if I were to look at the worst case condition, the biggest I could get is the size plus my geometry imperfection to give me 0.495. And my hole will be the smallest I can get, which is MMC, minus the geometric imperfection to give me 0.495. At this point in time, even at the worst case condition, I will still be okay. Now, what will happen if I don't come up with the worst case condition? Well, if I don't come up with the worst case condition, well, whatever I gave you before in my envelope, right, and I give you a little bit of opening for my envelope, I will grab my part, I will put it in there, and if my part did not come up to be the right size, and I move away from my top of my envelope, now I have more wiggle room. You guys see it? And this wiggle room now has this form imperfection that I can account for, right? So as I move away from my top of my envelope, whatever I give you extra, I got bonus, and bonus to be used for geometry imperfection. So, let me see, do I have something here? Yeah, pretty much what it says here. Now, you guys will wonder, how do I use this? How does this get to be used in practice? Right? Am I going to go every time and check every hole, every pin? Imagine how long that would take you, right? Especially on a derived medial line, that I have to go 3 million times to derive that line, right? That would be crazy. And then you got to do 3 million pins and 3 million holes. So that would be crazy, right? So how do I use this? Well, I can do something that we call it a functional gauge. Use a piece of metal, like a pin, that it is get to be measured at the worst case condition. So if I have, remember, the worst case condition for a pin is when my pin is the smallest. I mean, the hole is the smallest, right? The worst condition for a hole is when my hole is the smallest. Taking away the size and taking away the imperfection. The worst case condition for a pin is when it's the biggest and it's the crookedest, right? So let's go to the worst case condition when the pin is the biggest and the pin is the crookedest. And let's come up with a hole that has that condition. Okay? Now, this hole is at its worst mating condition. The biggest and the crookedest. Let's grab our pin and let's stick it there. Now, if the pin is at the worst case condition, it will barely pass. But as my pin is moving away from the worst case condition, we will have wiggle room, right? And it will have wiggle room all the way to the LMC. Remember, you have LMC, you have MMC, and you have geometric imperfection. Your tolerance plus whatever wiggle room that I gave it because I opened my envelope. And the envelope that I open it so you can get geometric imperfection. That make sense? So this is what you guys see here. 1 plus 0.1 plus 0.005 will give you 1.015. The worst case mating condition for that pin. And as I move away from MMC, the worst case size condition, I get extra bonus move within it. For a hole will be something similar. For the whole, I will also find worst case condition. 1 minus 0.01 minus 0.005 will give me the worst case condition. So I can grab, this is my part, grab my whole, stick it into the gauge, which is the worst case condition is increased. And I don't, at this point of time, I account for both. Because I'm building things at the worst case mating condition and still mating it. I don't have to measure at the right median line. It's already in the gauge. Does that make sense? Wilfredo? Watch the video 3 million times. Okay, now let's put it in the. I think I have a cheat here with the math. Have a cheat sheet with the math. Actually, I don't have a cheat with them. Okay, let's quick review. When you have a part, you are bounded to size by default, right? That is, in fact, rule number 1 of GD&T. Your book, the standard that I have in my office, by itself is telling you, you know what? I am going to bound you. You're going to be bound by the worst case mating condition, which is your MMC. Rule number 1 states perfect form at MMC. Perfect form MMC is kind of like an envelope that you are bounded, so your part can only deviate up to MMC. For form variation, the maximum you can get is the top of the envelope. When you put a straightness on a feature of size, you open up the envelope. But you open up the envelope based on the geometry imperfection. How much you want to give it to them, right? It's going to depend on function, how much you're going to give it. Once you open the envelope, you slightly raise the size of your envelope. Now your part can go inside, and if it comes at its maximum material condition, you can only have this little extra in terms of imperfection. But if my part gets away from MMC, it's a little bit smaller. Now I have a little bit extra, which is bonus, plus whatever I gave it at the beginning. So I get all of this for form variation. Remember, this guy still has to be above your least material condition, right? LMC. You are bounded from your maximum and your minimum. Does that make sense? Hopefully. Okay, so next time we go meet, you guys will have another quiz. Not on this. We'll start slow, right? Like get you a little bit. I will grab your bike and I will carry it, right? And then once I see that you guys can understand form and orientation tolerances, then I'll start jumping you into position. This is to prepare you for position. This is not position. This is your straightness, right? So I would say review what I just talked to you guys about. Make sure they can grasp. So next time we talk about position, you guys understand position. Otherwise, everything's gonna be like blah 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 blah. That makes sense? Watch the video 20 times and you'll get it.